Hello everyone and welcome to this lecture. Today we want to talk about how we can declare and deal with matrices in Wolfram Mathematica. So we know that matrices are just array of numbers, right? And in the programming language we can declare array. That is something we also know, and in Mathematica you have to declare array in terms of list. So let's get started. So let's say I want to declare a matrix called A. And what I want to do is that first you have to put two braces, and this will tell Mathematica that whatever the entries are here are actually lists. So let's see. Let me type something like 1 to 3. If you run this, you can see that Mathematica took it as a list, and you can see some options, that is total, mean, max, reverse, and more. If you click on more, you can see all these options over here. So if you just click on rotate right, it will rotate it right. So instead of list, what we want to do is that we want to have our matrices, right? To do that, we have to declare list under a list. For example, if you just take this and you want to have a, let's say, a column matrix. So you can type in matrix form, and you can see that Mathematica automatically took it as a column matrix. Or what you can do is that instead of writing matrix form there, if you want to use it as a column matrix, just write matrix form over here. Run it again, you can see that this is working very nicely. But what if I want to have a row matrix, that is the row, the transpose of this thing, right? So what you need to do, you have to type transpose, and inside this just type A, and you can see that it's showing the transpose of A is just like this. But we are not seeing the 1, 2, 3 in a row format, right? So to do that, what you can do is you can see that over here, the transpose the list. So you have to provide the list, not the matrix form of it. So instead of the matrix form, you have to get rid of it now. So by default, it will take it to be a column matrix. So let me write A again over here, and you can see that, okay, the first two levels of 1, 2, 3 cannot be transposed. So this is just a warning, nothing else, because what is happening over here is that you are not exchanging your 1, right? So that's why it's just a warning over here. Let's now go on and declare matrices. So instead of a 1, 2, 3, I want to have a 3 by 3 matrix, for example. Let's call it 0, 1, 3, and I want to have X, Y, Z over here. The reason I'm doing this is to show you that Mathematica, as you have seen in the past lectures, that Mathematica can handle symbolic calculations as well. And if you run this, this is the thing you'll get. And as you can see, Mathematica already assumed that this is a matrix. Use a list of a list instead. So he's saying, if you want to have a list of list, if you want to just you do that, you want to click over here, and you can then display grid, table, matrix. You can calculate the determinant, you can calculate the inverse. But let's try to see it in the matrix form first, whether whatever we are writing is making sense or not. So just type matrix form, and you can see, yes, what Mathematica did is that Mathematica took them now as row matrices, and using that he just puts one row after another, and you can have a matrix like that. So now let's declare another matrix. Let's call it B, and when let's just take some complex numbers in B as well. So first entry is 1 plus I, second is 2, third is 0. Similarly, you can also denote the imaginary unit as capital I. Mathematica will take it to be the imaginary unit because this symbol is protected. And I want to take a symbol, I want to take another symbol, and let's say I want to have a symbol plus number like this, and lastly I want to have 2, 3 and another symbol, let's say G. And if you run it again, okay, this is a successful run. But now what we want to do, we want to add these two. If you add these two, let's see what happens. You can see that this is the thing that we would expect. So if you want to see it in the matrix form, just type this matrix form, and there you have it. What if I want to multiply these two? So I will just have to type A, and the standard matrix multiplication is defined with a dot. So you put a dot B, and again I want to see it in a matrix form, so, and there you have it. Mathematica handles successfully everything. You can also choose to evaluate the determinant as this. If you just click on the determinant, it's taking all the elements over here, that is A dot B. But you can do it in a more shorter way instead of writing like this. So let me get rid of these things. So what you need to do is that you need to get rid of this matrix from over here, because when you do that, Mathematica won't be able to handle them like list. So you want to type deter you have to type this det, and you type A dot B over here, so it will multiply AB and BA, sorry, just AB, and then it will evaluate the determinant. Again, you can see this is my determinant, right? So it's a pretty long determinant, and Mathematica gave it a very good answer in a very short time. If you want to have simplified, just click on simplify and so on. You can also evaluate the trace, let's say tr trace. If you put your cursor over there, what you can see is that it's not showing me anything because it might lag. So find the trace of a matrix or a tensor that is entered as a list. So let me just have the trace of A, and it is 2 plus Z, as you would expect, 1, 1, and okay, and Z over here, exactly. Similarly, I can also take trace of A dot B, right? See, this is my trace, this is my determinant, and this is how you can easily do anything you want with Mathematica. That is, you want to manipulate matrices. If you want to have inverse, you have to type inverse, and if you put your cursor over there, it gives the inverse of a square matrix. So just type A and you will get A inverse. This is your A inverse, and just to be sure this is A inverse, what you need to do, you need to multiply A dot inverse of A, and let's see if we get the identity matrix. Okay, it's showing that no, it's not identity or something like that, right? But it should be identity. So what is happening over here? That is A dot, and if you just type full simplify, you can see that this is indeed the identity matrix. So sometimes Mathematica won't simplify things, sometimes you have to use this full simplify and all that. And if you want to see in the matrix form, again just type matrix form. There you go. So this is how you can easily declare and do stuffs with matrices. One thing I would like to show you right now is that what happens if you type A times B, that is a multiplication. So you can see something weird is happening, and if you just type in the matrix form, you can see that something very weird is happening. That is, it is not the standard matrix multiplication, and the resulting matrix have a 1 plus I, that is over here, and 4 in the second entry. So what is happening is that it's not taking the standard matrix multiplication, rather something else. So this is not the way to do it. This is not the way to multiply matrices in Mathematica. And if you use this, what will happen is that it will assume that their list, and it will assume that they are kind of sets, and it will return to you the Cartesian product. That is, 1 will multiplied with 1 will get multiplied with 1 plus I, 2 will get multiplied with 2, 3 will get multiplied with 0. And as you can see, this all of this makes sense when you look at this row. Similarly, for the second row, 0 will get multiplied with I, which will give you a 0. 1 will get multiplied with t, that should give you a t, and 3 should get multiplied with v plus 5, which should give you a 3v plus 15. And this is the thing that is happening over here. So this thing is actually a Cartesian product. So this gives you a Cartesian, similar to Cartesian, not the exact Cartesian, let's be careful about that, similar to a Cartesian product. So in case you want to have a Cartesian product, you can use this, but always you need to know what you are doing and what operation you are typing in Mathematica. So this will be it for today, and I'll see you guys on the next lecture. Thank you.